Hello, good morning to all. My name is Mohammad Umair, and my thesis title for today's presentation is Federated Learning for Network Intrusion Detection with Dynamic Aggregation. My supervisor is Dr. Fu Yilu and co-supervisor Dr. Tanvi Hao. These are the important dates. So I registered in June 2022, and then I passed a research methodology and commercialization entrepreneurship course in at the early 2023. Similarly, I passed my proposal defense at the end of 2022, and I did my work completion defense in June this year. Now, talking about the Internet of Things and IoT, IoT can be defined as a network of devices that are connected to internet and that enable communication and data exchange together. IoTs nowadays it's transforming everyday life in and various industries through connectivity and smart technology. Some of those famous applications for IoT are applicable in smart homes, healthcare, manufacturing, and transportation industry. With this rapid growth of IoT, there comes the challenges as well. The most common one are related to security concerns, which are related to cyber attacks and data privacy issues, interoperability, ensuring the compatibility of different devices so that it can communicate together, and then handling a vast amount of data efficiently comes under data management. Because my thesis is related to cybersecurity, so I have deal with the security concerns problem, and I'm gonna do my I did my work on this area. So nowadays we see increasing threats of IoT attacks. The threat landscape of intrusion attack is constantly evolving and increasing on IoT devices. There's need effective classification models that should be able to differentiate between benign, which is a normal, and malicious attacks with dynamically evolving patterns of those IoT attacks. Conventional machine learning and deep learning methods have shown their promising and shown their effectiveness, uh, uh, shown their good performance, but their effectiveness is limited because of the privacy concerns in a centralized environment. That is where the dataset needed to be collected on a single device. Talking about different types of attacks, the famous one are botnet attacks. Botnet attacks can be defined as a network of infected devices controlled by a malicious entity, and then it causes data theft, spamming, and unauthorized access. The second most common one is DDoS attack, which is distributed denial of service. It do overloading into a target system with a massive traffic, and it cause a crash or make the device become unavailable. It disrupts services, leading to a downtime and potential financial loss of the entity. The third and most common one is Mirai malware. It targets IoT attacks as well, and they transform from the botnet attacks into a large scale with the combination of large scale DDoS attacks, and it compromise device security and exploit default credentials of the user. Now, in order to detect these attacks, there are existing methodologies. The famous one is the traditionally used one is signature-based intrusion detection system. So, in signature-based intrusion detection system, there are predefined patterns which we call it signature. It contains patterns of different attacks, and whenever a new data comes in, using that signature database, if the pattern matches with that one, only then the system gets activated and it sent an alert to the user that there's is being an attack detected. But they are inefficient against the unknown attack, even because they are pattern based traditional methods. So if any single pattern, if anything has been changed in that pattern, or the attacks have evolved nowadays, the attacks are also being evolved. So then this technique become insufficient to detect those attacks. Then there's other one which is machine learning and deep learning based intrusion detection system. Varies, and they are in here we use a lot of data set with different models to train and to learn to make the model learn on different types of attacks and pattern. And then they require a lot of data set to be accurate in a centralized environment. Talking about centralized environment, so because machine learning and deep learnings, traditionally machine learning and deep learning techniques comes under centralized system. For this one, the data needed to be collected at one node or at one machine to identify the attacks and to train the model as well. It can then it can expose the sensitive information and weaken security because those enterprises and many industries they don't want to share their private data. So uh, it still cause data privacy issues. Then usually in this centralized environment, the data set is collected from a single source data set, which makes the model to perform not effectively when a data set from a different source comes in. And then it lacks the capability of providing accurate results when tested in a different environment. It created a need of a decentralized approach. So in decentralized approach, federated learning was the most common one, which was being introduced back in 2016 by a team of Google. As we can see in the figure, so the workflow of the federated learning is that we have a different multiple clients, or we can say multiple user, where they have their own data set on their devices, and then using the server, the local model can be sent to the client side, and it can be trained into the end user side. Using this one, we can integrate thousands of millions of clients to train the model to be effectively trained on it. Because this was introduced by a team of Google, so nowadays the application of federated learning is Google search, where Google search and Google next word prediction. So whenever we search on using Google keyboard, a next keyword being suggested by Google, that is a practical application of federated learning. Now, in federated learning, because the model is trained using multiple clients, so aggregation is the thing that needed to be is one of the most important thing in federated learning. Local training meaning that clients train on local data, and then for the model updates, the clients need to send their updated model weights to the server side so that the global model can be aggregated. For aggregation strategies, there are different aggregation strategies that are crucial for optimizing model performance in federated learning that ensure robust and accurate network intrusion detection. Now, many researchers are working on this area and they are utilizing federated learning for network intrusion attacks. So, as we can see, the author reference 7 has utilized CSE dataset and used dynamic weighted aggregation technique with federated learning along with the different number of clients and achieved the following classification results with an accuracy of 94%. Similarly, the author of reference 8 used NB-IoT dataset for the attacks classification, and in his case, he used clients as UAVs, where he achieved an accuracy in between 92 and 95%. Similarly, on reference 9, the author has used a personalized Fed averaging techniques with client number as 5 on a different number of rounds and achieved an accuracy of 96%. Furthermore, people are also using transfer learning concept with federated learning, and because author 10 has used a similar concept, federated learning with a transfer learning, and achieved an accuracy of 92%. And then reference 11, the author have used federated learning techniques with Fed averaging, and on a test dataset which was being kept unseen for the whole scenario, achieved an accuracy of 68%. Similarly, another author have used UAVs as their client and achieved an accuracy of 90%. And then in the last one, the author has used NB-IoT dataset with integration while utilizing CNN as their global model and achieve an accuracy of 87.45%. However, the only author number 1 has used a dynamic weighted aggregation techniques because this technique was introduced by this author, so it is still a newly proposed technique. And the other researchers have using Fed averaging techniques, which is a traditional federated learning um, workflow to implement federated learning algorithms. Now about the problems with federated learning, because the aggregation of local model from varying clients in federated learning based algorithm, it still remains a significant challenge about how to aggregate a model which comes from a different number of clients. And then in federated learning, poorly performing local models from clients, they negatively impact on the performance of the global model. It causes fluctuation in accuracy, leading towards a overall poorly performing global model. So, the problem statement for this study is that traditional methods like machine learning and deep learning, they depends on a centralized data storage and processing, raising a privacy concern. Federated learning, however, has emerged as a promising decentralized solution by utilizing machine learning and deep learning models to be trained on our distributed data sources without sharing data. However, the aggregation of local models from distributed clients in FL algorithms remains a challenge. Addressing these challenge involves improving the performance of a network intrusion detection system for dynamically evolving IoT attacks, investigating the aggregation process in decentralized environment, in decentralized training, and enhancing the model performance through deep learning techniques. So the research objective for this study is to utilize the network intrusion detection model for dynamically evolving IoT attacks to propose an effective decentralized approach to improve the trained model performance of network intrusion detection system for IoT attacks and to investigate the aggregation process for decentralized training with deep learning model. So, because we are dealing with IoT attacks, so the dataset that are being used for this study are the two most famously used one, which is NB-IoT dataset and CSE dataset. The NB-IoT dataset consists of network traffic data gathered from 9 commercial IoT devices, which were authentically infected by Mirai and Batchlight attacks. On the other hand, CSE dataset it contains 7 different botnet attack scenarios such as brute force, botnet, DUS, and web attacks, network infiltration. They were also collected from different IoT devices. About the NB-IoT dataset, so these the devices that are being used were some of those like cameras and then alarms and then security purposes cameras was also used where the attacks were specifically injected into their environment and then data was being collected. The creator of this dataset, they have made this dataset publicly available for the research purposes. And upon assessing the data distribution of these different types of attacks has been shown in pie chart, which can be seen as the dataset was not balanced. About the CSC dataset, so the CSC dataset was being injected using Amazon Web Services AWS environment, where different environment was created, and each of those machines were specifically connected to that specific environment, and then again the attack was being injected into their environment to make those devices affected from those devices, and then dataset was being collected. Similarly, here too in the pie chart, we can see the authors of this dataset has also made this dataset to made publicly available to everyone for research purposes. And upon accessing this dataset, the pie chart shows that this dataset was also quite imbalanced because the web attacks contains very less attacks, approximately 0.04%. However, the DUS attacks and DDoS attacks contains the majority of the collected dataset samples. So the methodology that are being used is that we use these two dataset, and then firstly we did a model selection. For the model selection, we use spiking neural network and convolutional neural networks. And after selecting the best model from these, then we implemented federated learning into the using the best model. And on that, after then we have used the dynamic aggregation techniques into that dataset. About spiking neural networks, so spiking neural networks are a class of a neural networks that are being inspired by the behavior of biological neurons. And unlike traditional neural networks that use continuous activation functions, spiking neural networks communicate through discrete and sparse time-varying events known as spikes to communicate between information between different neurons. They are very light in nature because they just only send information using different spikes. Compared to spiking neural network, convolutional neural networks are mainly used in deep learning. They are consist of multiple neurons, and then each neurons are assigned with different weights. The weights are being usually trained during the training process, and then we use the activation functions, different activation functions like ReLU, softmax, sigmoid, and many others exist as well that can be implemented in these convolutional neural network classes. So for the model selection, we because spiking neural networks was also recently introduced neural network. So we use spiking neural networks and convolutional neural networks for the model selection. Traditionally, the authors have using 1D CNN in their previous research for IoT attacks classification. And then, upon implementation, we came to know spiking neural networks achieve an accuracy of 71.94% compared to CNN, which achieved an accuracy of 98.96%. Spiking neural networks, although they train very faster, but they work on a spike. So training those spikes was quite difficult because they are very sensitive, and each of those spikes have to be trained whenever some certain event has been triggered, and then they are very sensitive towards the hyperparameters. So achieving a better accuracy with spiking neural networks make them difficult as well based on their mechanism that they works on. And then on convolutional neural networks, we achieve an accuracy of 98.996%. So for the federated learning methodology, we utilize this methodology where we have our data pre-processing techniques. In data pre-processing techniques, we did the data cleaning, data normalization, and then standardization, and then the categorical transformation of those output attacks. Upon then we used feature selection methods using three different machine learning models, the random forest, XGBoost, and XRT classifier, and from them important features were being extracted, and then we did the data splitting into train and test. Then the next step was to distribute the data among those clients. The trained dataset was used and it was being distributed equally to the clients. And then we used the dynamic federated learning methodology into those clients. The model was being sent to those clients where they contains the trained dataset. And then the model was trained. After then, the aggregation process comes in, and then we use the global model for the model evaluation purposes on the test dataset. So, for the federated learning implementation, we use CSC dataset and NB-IoT dataset. For this case, the results being shown is for CSC dataset, and here we achieved it 7.98%. And we studied an effect of different clients, how it affects on the accuracy of the of the model. So we see that using the FL methodology with different number of clients, we achieved highest accuracy of 94.2% when number of clients was kept as 10. We also compared this methodology with traditionally used Fed averaging methodology, where the highest accuracy achieved was 88.3%. Now about the dynamic aggregation. So for the dynamic aggregation, we introduced that we use validation threshold accuracy. The model need to be trained on client side first, and then it need to go into the validation accuracy threshold values. Upon then, the aggregation of different models will be combined together, and then it will update the global model weights, and then those global model weights can be utilized. Algorithm shown here shows an workflow of this methodology where each of those clients need to be trained on their respective data set first, and then because even the client data set was also further split into train and validation, and then that client data set and then that client model will be evaluated on the validation data set into the client. Upon evaluating, then the local model was being sent to the validation threshold accuracy, and then if it achieved threshold accuracy more than given threshold accuracy, then these parameters will be sent for the aggregation process where the aggregation will happen, and eventually it will update the global model weights. We use 1D CNN model architecture as shown. Here we use four convolutional neural networks along with a max pool, and then two following with two dense layer and output layer. So the detailed methodology for the proposed federated learning framework is shown here. So, firstly, we did the data preparation as discussed. Like for the data set, we did the feature selection. For feature selection, we use the machine learning model, the most commonly used one, which is random forest, XGBoost, and extra tree classifier. And from here, we extracted top 20 columns because uh, originally the dataset contains more than 100 columns for both of them, and then it contains millions of samples. So feature selection was very important for us to extract just important features only which are impacting those output class. So we use machine learning models to extract top 20 columns, and then once those top 20 columns was being extracted, then we did the data normalization, and then that data normalized was split into train and test. The test dataset was separated from here, and then further we use the train dataset, 80% of the train dataset, and we use that train dataset to be distributed among those clients. And then further in the clients, we further splitted that 80% of the training dataset into training and validation, so that those local models can also be evaluated on the validation dataset for each of those clients. We proposed a dynamic federated aggregation techniques which works in a hierarchical manner. Firstly, a random global model weights are being assigned towards to the clients, and then because the clients contains their respective dataset already, so the local model was being trained into the client dataset, and upon training, then the model was being evaluated into the valid data set. If the model achieved accuracy of greater than 80%, only then the model was being sent forward for the aggregation process. However, if the model achieved an accuracy of lesser than 80%, then it was being sent back to retrain again, because the poorly performing model will eventually affect on the aggregated overall aggregated model. So we don't want to use those models which are performing poorly because of the model overfitting or underfitting problems. And then if the model achieve an accuracy of greater than 80%, then those trained models were being dynamically aggregated together. And then upon then those after the dynamic aggregation process happened, then the global model was being updated, and then the test dataset that we kept unseen, the global model was being evaluated into the test dataset. So about the results, so these are the features selection results. So when we use random forest, XGBoost, and extra tree classifier, each of those models they extracted in the same manner. So the top 20 columns were being extracted from each of those models was the same. It's only that the importance score was different with respect to each of those model. And then we used it for both of those dataset, NBIOT and CSE dataset. These are the tables for the train and test splitting. As we can see, we used 11 classes of NB-IoT dataset and then 6 classes for the CSC dataset. And then further, we divided these dataset we equally to each of those clients. So each client contains equal number of samples into their database. So the dataset was sent to those clients was quite balanced. Upon training, these are the learning curves for each of those clients that have been used. These each client was trained for 50 number of epochs, and then it shows that the model was being converged, and then um, the loss was kept decreasing until it became stagnant at one point. And then these are the learning curves for NB-IoT data set here. We can see that some of those clients are performing poorly and a lot of fluctuation was being happen here. And then for each of those clients, we also have their respective confusion matrices here. I didn't presented all of those confusion matrices here just to show like for each of those clients, we also achieved a confusion matrices as well. And then these are the results that are being obtained for each of their respective clients for NB-IoT and CSC dataset. The parameters that are used are precision recall F1 score and accuracy here. So overall CSC dataset was around somewhere around 80 and 82% of an accuracy, and NB-IoT dataset was between 96 to 99% of the range for the client. And then upon aggregation, the overall global model performance is obtained on test dataset is as follow. So we achieved an accuracy of 98.94% on global model for NBOT, and for CSC respectively we achieved 81.05%. And then we gave a class-wise classification report of each of those attacks respectively. So these are the comparison with the other studies. So one of the paper that I have published in one of the conference. So the table shown above shows that overall we achieved an accuracy of 87.98%. We used dynamic aggregation techniques. Faisal et al. However achieved an accuracy of 90%, but it was using Fed averaging techniques and without dynamic aggregation. And then another comparison table has also been given here. So here we see that Popela et al. Has achieved an accuracy of 99% plus minus 0.6 with NB-IoT dataset. He used 5 classes, while number of clients kept to be as 5 as well. Chandra have achieved 87.45%. Number of classes was not clearly defined in his paper, and also aggregation techniques wasn't being defined as well. Ray et al. Used 2 classes with NB-IoT dataset only and achieved 99.42%. Lee et al., who proposed the concept of dynamic aggregation, he achieved an accuracy of 94.58% on CSC dataset. And in our proposed work, we achieved an accuracy of 98.94% overall. The overall comparatively good enough compared with other. And CSC dataset, we achieved an accuracy of 81.05%, which is still lesser, mainly because the pre-processing techniques that we used were kept common for both of these two datasets were used as the same. And then the conclusion is that we have explored the implementation of federated learning with dynamic aggregation approaches to classify intrusion attacks on IoT devices using different model architectures such as spiking neural networks for feature extraction and 1D convolutional neural network. And then along this, we propose a hierarchical federated learning framework that dynamically aggregates the global model with a threshold accuracy. The limitation and the future work, the limitation is that we have used a balance. We have distributed the dataset balanced and equal number of sample to each of those clients. So Varying data distribution strategies will impact on the overall global model performance. And then the global model still contains sensitive information, and then those maliciously or poorly performing models can affect global model convergence furthermore as well. Future work can be to explore different data distribution techniques to enhance the model robustness, to develop method to ensure global model doesn't leak sensitive information, implement a diverse privacy preserving algorithm to secure communication during FL, which happens between server to client side. And these are my publication list. These are the references.